Okay, so great job on the quiz, everybody who came. All 4 undergrads. Uh-oh. If you would be so kind as to, since we're going to start lecture now, if you'd be so kind as to write your name on a piece of paper and a fun fact. Just any fun fact. Anything. It's worth 50 points. If you could do that right now, please.
Okay.
Yeah. Figure if less than half the class shows up, and the people who show up should receive some sort of bonus. Okay, so up until this point in section 9, we have kind of covered the multi-cycle data path. And what we're going to be covering for the rest of the lecture is you've designed your data path, you have your VHDL. What happens when you put it into your design tool to actually fabricate a chip? So we're going to be going through this whole process here, and this is kind of the general overview of how this process works. So you write your VHDL netlist, or it can be SPICE, right? And so you're synthesizing it down to your technology. So you, for your labs, you're using 0.6 micrometers, micron. Goes down to the different transistor level. And then what's going to happen is it's actually going to be, we're going to be talking about this today, it's going to be covering the concept of floor plan. How are you actually laying out the chip in a way that is power and space efficient? From there, we're going to be talking about various what are known as load constraints, meaning that you have to, when you're laying out different blocks, you have to ensure that the routing can be achieved in a certain way. You don't want, we already know about overlapping wires. We already know about, for example, Miller coupling factor. When you synthesize it in a certain way, when you're wiring it, once you've wired cells together, you limit how they can be laid out. Right? So basically what you're going to try to do is we're going to counter something called T junctions. These are very common, where you have a short stub T and then the long part. You want to synthesize this first so you can bring them as close together and then deal with the other portion. Because if you deal with this and it's long and you mess with that, then you incur area overhead. So then, now we worry about timing. Everything has to be laid out in a specific way in order to ensure that it meets performance metrics. And then from there, you're actually going to synthesize the chip. And from there, you're going to do something called place and route. And then the last thing we're going to do is called tape out verification. So Coleman, can you do me a quick favor since you're here? Take out a piece of paper, write your name on it, and any fun fact that you can think of. Just something fun, like, for example, elephants are the only mammals that cannot jump. Or today is Thursday, April 16th, 2015.
That's not a fun fact.
And so, yeah, it's not that fun. My cutoff is 11:10, so for those of you who are still not here, after 3 minutes, they walk in, they're lost. So if you could do that for me right now, please. All right, so here are these steps actually laid out. Design entry, to input a logical description with no physical information. So here you're talking about some sort of VHDL, Verilog, or SPICE. In SPICE, what it's going to do is you're going to do your include file, and you're going to include this initial synthesis where you're including little to no information on interconnect loading. So if you recall from your SPICE file or your Verilog file, you're basically just saying they magically connect somehow, right? So you are basically saying, so you have your transistor 1 and transistor 2, and they lay out in such a way that they are supposed to work, but you're not actually including that information. The output of the synthesis tool is the input to the floor planner. So basically what the floor planner is receiving is this information that's saying, I have a certain number of transistors, I have a certain number of cells, I need to lay them out somehow. So this next step, 3, is the initial floor plan, which we're going to find. From the initial floor plan, inner block capacitances are input to the synthesis tool. So you remember in section 2 when we were calculating input and output capacitances of all these different sections? This becomes important in calculating the floor plan, because you need to ensure that you can properly drive everything, but you don't want to consume too much power with your nets. As the nets increase in length, they consume more power. So you have to take all these into consideration when deriving your floor plan. Into the tool as load constraints and inner block capacitances are input as wired load tables. So what this means is you have different wires connecting, so you have different cells that are output, right? So and then you're connecting them with wires based on your inputs and outputs. A better example is you have your data path in your controller, right? And you have all these wires going back and forth, your IRD, you have your PC write condition, you have your ALU op A, ALU op B, and all these wires need to speak back and forth, right? So they have to have and each of them are driving a specific portion of the data path. It's either driving your ALU or it's driving your data memory. All of these have different requirements. And those are considered as load constraints in your synthesis. The synthesis tool produces a forward annotation file to constrain path delays in the placement step. So we calculated path delays in section 4, I believe. We calculated path delays in section 4. So at this point, the synthesis tool is going to take your SPICE file or your Verilog file and do that work for you. But you are dependent upon the tool because it's going to make trade-offs based on your constraints. Timing-driven placement. As I've kind of alluded to, we have to meet various PVT corners. We have to meet these design corners that we talked about in section 6. So timing-driven placement deals a lot with performance and how that applies to the specific slow, fast design corners for PMOS and NMOS. And we'd say after placement, using constraints from the synthesis tool, the location of every logic cell on the chip is fixed, and accurate estimates of interconnect delays can be passed back to the synthesis tool. So at this point, we have now placed our cells out onto the floor plan. We have connected them using interconnect wires. We use these load capacitances that we've calculated, and we create this forward annotation file, at which point we then test our performance. We test our performance. Can it meet noise margins? Does it, if we go too fast, does it meet our power constraints? All of this ties into timing. Can we do this as fast as the customer wants? So then next thing we have to do is we do this thing called synthesis with in-place optimization. So now we're trying to optimize it. So now we have everything kind of laid out. Now we're seeing where optimization is going to occur. So we say here that the synthesis tool changes the drive strength of gates based on the accurate interconnect delay estimates. So before we had all these gate sizes that we used based on previous calculations, but now we know those exact values. So based on that, we can actually change the sizes of the gates and see since we know if we can reduce the size of the gate, we'll still meet our timing requirements. And so last but certainly not least, detailed placement, actually writing it out. The placement information is ready to be input into the routing step. So what this means is now, so the kind of general overview is here. So you have your net list, which you can do by using either VHDL or Verilog. You do some sort of paste, place, and route. Now, you do parasitic extract. What that is you're actually testing the parasitic capacitances of all of your transistors, all of your wires, and seeing and minimizing that as much as possible, because as we know, that contributes to reduced ability to meet timing constraints. So here, once we do that, then we actually test our timing. If it doesn't meet, then we go back here and rework everything. So it's a flow chart. And then next, once we meet our timing analysis, here we're testing noise and reliability. And then if it's okay, we can then send it off to a database manufacturer, for example, MOSIS, which we talked about earlier in the course. Yes, Terrence.
On that slide, why does it go from net list to noise reliability as well?
Yeah. Okay, so that's a good question. I'm going to attempt to make an educated guess. I don't know the 100% exact answer. But my educated guess would be that as we're kind of looping back and forth here, we can if we're not doing, I don't know. Every one I've ever done has to go through all these other steps, so I can't think of an instance where you wouldn't be doing that.
Do you think it's because you didn't meet your timing constraints?
Oh no, this is if you go to the timing constraints, you're going back to place and route. There's no backup to the net list. That was the first thing I was trying to think about. That was my first guess, and then like, wait, that doesn't not there. So I will look it up, and I'll have it answer you next lecture. Does anybody have any other questions that will stump me? All right, in that case, we're going to visit this concept of floor planning. So if you recall, I've shown you this diagram a couple of times already. And what's going on here is we have, this is our data path is then put into this block, right? And then we have our controller put into this block. And what the floor planner is going to do is it's actually going to try to optimize the area by making the data path and controller the same width. And here it set them both at 2,550 lambda after the synthesis tool is complete. So now here, I should also point out, wiring is 25 tracks of 200 lambda. Now we have 13 control signals, some of which have more than one input-output. And we're going to also be using state transition signals as ways to communicate back and forth between the data path and controller. So the total number of wires that are going back and forth between the data path and the controller are, so it's 25, and we have calculated it out such that the wiring tracks are 200 lambda long. So the reason it's doing this is because now we're calculating how long the wire needs to be in order to properly drive all the different aspects of the data path. And so here inside of the controller, so this is the floor plan of the controller. So we're getting inputs and outputs. So we have all of these different signals. So here we have write data, mem data, addressing, and all of these bit lines that are, I'm sorry, yeah, these are coming into the data path. So these are now all manipulating based on our bit lines. So we have 8 bits, so we're doing 8-bit slices into the data path. So we're trying to have it go out. So now we have all the control signals coming through. And then as the 8 bits are going through the specific portion of the data path, you can then say, all right, well, this control signal will manipulate in this manner, and this control signal won't manipulate it in this manner because this is 0, and so forth. So that's how it uses these control signals to be able to implement the multi-cycle, because as you're going through each portion, as it moves to the next buffer, do we need this or do we not? If not, it can go straight through that portion of the data path and move on. If so, it'll be manipulated here. And so you can actually see here, like if you have the memory data register, your write multiplexer, your register files, source B and source A for your ALU. So then there's an arithmetic logic unit. Here we have ALU out buffer. Here we have the program counter. I'm sorry, well, here the ALU's over here. So these I kind of move back and forth. So you have source B, source A goes to ALU. So as you can see, the program counter goes back. And this layout is done in the floor plan for optimization. So even though we're drawing it out, we have the program counter, which goes to our memory, which goes to our register file and our ALU, because that's the data flow. That doesn't necessarily mean that that's how it's optimized. Because let's say you have, you can put your ALU here, and if you can minimize the wiring based on your capacitance driving, your parasitic capacitance, you can then kind of fit it into this kind of square area. So you can see how it's kind of into, like they have the ALU over here, the program counter here, you have source A, source B, your registers, and then your IR3210, which we talked about, your instruction write 3210. any of the different muxes in between to regulate the multi-cycle implementation. And so what we're going to do here next is we're going to formally define this concept of floor planning. It's a mapping between the hierarchical net list, which is our Verilog, VHDL, SPICE, describing the circuit and its physical description with the primary objective of minimizing the chip area and minimizing delay. And so a floor planning algorithm will accomplish the following tasks. It'll arrange the blocks on the chip. It'll decide the location of the I/O pads, which we're going to go into the design of these pads later in this section. But basically, what you want to do is, if let's say you have your 8-bit input from your controller, right? If I'm gonna scroll up here for a second. So you don't want a pad up here controlling an output that comes down here, because now you have to go all the way around, right? So you're now maximizing area and you're maximizing delay. You want it to come here. So you have pads you're going to have known as power pads. You're going to have VDD and ground. You're going to have power rings, which are going to properly regulate how the power is distributed throughout your circuit, because you have to worry about clock tree synthesis. So part of this floor planning algorithm is you have to decide which I/O pads are going to be used for what purpose. So you have to decide the location and number of the power pads. We'll formally define these later. But in short, VDD and ground. Decide the type of power distribution and decide the location and type of clock distribution. So power distribution and clock distribution are important factors in being able to minimize your area and your delay. Because as we've now learned, that dynamic power consumption is a significant driver of overall power consumption. And dynamic power consumption is driven by your switches from 0 to 1 and 1 to 0, right? Your switching factor is a huge is of huge importance in your overall power consumption. So the clock distribution, you want to minimize the amount of clock signals that are required to drive the circuit, especially in lower at a higher as we're scaling the transistors from larger sizes to smaller sizes. In the larger size transistors, the logic drove the amount of power consumption. But as we're getting to nanotechnology, the higher the clock distribution is a large driver of power consumption. So these become very important in the floor planning stage. And so I included this topical guide objective because this will be good for you to know when you do your lab. Your typical layout densities, your random logic is going to be 1,000 to 1,500 square lambdas per, and then you have data path, SRAM and DRAM in your ROM. So SRAM is your registers, your DRAM is your data memory, and your ROM is where you're storing it to your non-volatile memory. So per bit, and then your data path is going to be 250 to 750 lambda square per transistor, or 6 width length plus 360 lambda squared per transistor. Does that number look familiar? It should. 360 lambda squared. I'll give you a hint. It was a number on one of your exams. Yeah, we calculate 360 lambda, right? This is the constant we used to help calculate our IV curves to be able to calculate the sizing before PMOS and NMOS. You recall that we calculated the actual amount of current? And in order to do that, you had to calculate this number. So that wasn't just busy work. These all are meant to tie together. So this is actually, if you look back at your problem, you'll see that 360 was a number you calculated. Okay. Does anybody have any other questions before we move on to types of floor planning tools? Do you want me to, Jason, do you want me to? No, you should be good. Okay. So here we're describing 4 stages of a floor plan. So the initial stage is just generated by the floor planning tool, right? So we have 6 blocks here, right? And so what's going to happen is we're going to do this thing that we're going to figure out what's called a rat's nest. And it's going to try to wire everything together based on what we need, right? So it's going to see that, and it's going to say, how optimal is this? Right? So we just discussed all the floor planning steps, and we determine optimization, and one of those optimizations is interconnects, right? So if I delete these red marks that I just put here, you should be able to see the difference in the amount of wires between the initial plan and the final plan. So here, what they discovered, they're showing this little example, is cell B is just mirrored about the x-axis. Everything that was at the top is now at the bottom. Okay? And by doing that, they actually cut the amount of wires required to implement the circuit in half. Because now you don't have to, everything doesn't have to go around, you don't have to reroute things to make everything work. They actually, we're going to go over a real brief example of generating a clock tree here. But basically, this is a really good example of how you can use the floor plan to optimize area and power consumption. These 2 circuits, B and D, do the exact same logic, but D consumes significantly less power consumption and costs less because there's significantly fewer interconnects. Okay, so these basic layout approaches, which I've included here, I think at this point it's intuitive. For arrays, you're trying to get the basic cell, and then you calculate the number of cells. So if you're designing an SRAM array for a register, you design your SRAM, and then you need 8 SRAM in order to properly implement the register. And then you allow for area for decoders and column circuitry. And what that means is you have 32 registers, correct? So now you have to have 5 to 32 decoder. That's why our 5 bits from our value, from our instruction is coming in. You have to code that to 32 because that 32 bit becomes a word line to be able to determine whether or not we need to read to or write from it, correct? So these decoders and column circuitry to be able to make sure that you're properly driving with interconnect parasitic capacitance. You have to so you're meeting proper timing constraints. Then you have to worry about interconnects to make sure you're properly driving those wires, especially with memory. That becomes very. So data paths, we sketched the slice plan, which we kind of just described before. So up until now, we had never really discussed slice plans. Slice plans are you want 8 paths for each bit, and then from there you want to be able to optimize the interconnects to that path. You count the area of cells from the cell library, and then you ensure the wiring is possible. Seems kind of intuitive at this point. You might want to make you're designing community, you want to make sure that you can get to all the houses. Okay, so we kind of briefly went over this concept of abutment, which is aboutment unless you're Canadian. No. Abutment is establishing connections between cells by putting them directly next to each other without the necessity of routing, right? So floor plans is a floor plan with a property where composite subcells are obtained by horizontal or vertical bisection. So let me read out the rest of this definition, and I'll tell you what this means. A bisection of the composite cell. Slicing floor plans can be represented by a slicing tree. So we're going to go over this as an example. So abutment means that you have these cells next to each other and you're trying to wire them together, right? Now slicing trees are basically meaning how can we create the proper channels between these cells in order to ensure that we can get interconnects correctly. So a slicing tree means is that we can actually go from one edge of the floor to the other edge, and we try to cut it up into as many pieces as possible. And we're going to see an example of what happens if you can't do that, how you can move those around, and how you can use these slicing trees to actually optimize area. So here you have a number of wires going here. So you have your initial right in the middle. You can go up here and you can connect them this way. Here you can connect this cell, you can connect this cell. Here you have to go around this particular cell to get to these two cells. And then likewise you get to these cells just fine. So let me reread slicing floor plans. A floor plan with the property that a composite cell's subcells are obtained by a horizontal or vertical bisection of the composite cell. Slicing floor plans can be represented by a slicing tree. So for those, I don't know how many of you have taken an algorithms course or a graph theory course, but I'm going to go into very briefly into this concept of what's known as a minimum cut graph. So let's say you have 5 nodes in a graph, right? And so it's connected. The minimum cut of the graph is if you take a line and go through the graph and you're trying to hit as few nodes as possible where you can split it into 2 halves. Here, if you cut it this way, you're hitting 1, 2, 3, but if you cut it this way, you're hitting 1, 2, 3, 4 edges, right? So a minimum cut of a graph is a cut whose cut set has the smallest number of edges, which is what connects the nodes in the graph, or smallest sum of weights possible. We're not going to really go much into that in this course, but basically sum of weights means that you can weight the edges to say either you want to take this path or it's the path of least resistance. Where that applies here in this course is if you apply weights, you're basically connecting a number of wires. So you would apply a stronger weight to ALU off B, requires 2 wires, as than you would to I or D, which only requires 1 wire. Or if you recall from the ALU controller, it requires you have 2 wires going in, plus you have a set of 5 from your function in your instruction, and it produces a 4-bit value that goes to the ALU. So now you have a weight of 4 as opposed to a weight of just 1. So for those of you who took 385 with me or computer architecture, I was very adamant that you had to draw 4. That was a signal of 4. That becomes very important in reducing power consumption and providing your minimum cuts of your graph and your floor plan. So those of you, especially those of you taking 386, when you synthesize it onto your chip, the Xilinx tool, or you're using Vivado, right? So Vivado is going to provide a floor plan of what you're actually synthesizing to the board. So what it's actually doing is it's trying to figure out how to use your PLAs and lay them out in such a way that you can minimize area overhead. So it's kind of doing the same concept. Instead of the transistor level, you're actually using your programmable logic blocks to accomplish this. So the reason this is important is because we're going to be talking about this concept of congestion analysis. And congestion analysis is basically taking these slicing trees and seeing how congested the circuit really is. So before I read the definitions, let me zoom in on the graph here. So here, right, what's happening is we have two layouts of, we have 2 floor plans that we've obtained from our net list, right? And so here, what's happening, if you can see 200, 100%, and 50%, it's actually analyzing the amount of wires that are required if we lay it out this way as opposed to this way. Now, based on just visual observation without any scientific backing, we can conclude that this layout is better than this layout, where we have made the C longer, C cell longer, because it requires a greater routing congestion, which means greater wire density. So here we can see we actually have a kind of a cut here, we have a cut here, whereas by lengthening out C, it's harder for us to be able to make these trees. Now, if we go back to that previous diagram, if you recall, we actually kind of put a node in the middle and we were trying to get to here and here. So here, if we put this node here, it becomes easy to access all the cells, correct? If we put that in a spot, Well, in order to get to C, we actually have to go around E and then split it up to A. Same thing, we have to go to B. D and F are the same. So there's a result. We actually have a higher congestion, and that's caused by elongating the cell, which prevents us from being able to get to the other cell. So that creates this concept of congestion, which we'll formally define, or I'm sorry, congestion analysis, as the determination of the relationship between cell placement and the required interconnects. So you see how that definition ties into what we just saw? We see the cell placement, we see the cell size, and now we see how that affects the amount of interconnects we need to implement the logic. So the routability of the channel is the relationship between the number of interconnects required to implement a specific layout and the channel capacity. So congestion analysis is what we're doing, and routability is the measurement. And then the die cavity, I wanted to formally define this. So at this point, we've been talking, we have all these pads, right? And then we're putting in some sort of logic circuit. So in this case, you guys are doing MIPS. You have your controller and your data path, and they're going to your power grids, or you're going to your different I/O pins. The area inside of that is called the die cavity. So when we get to the end, next Thursday will be the last regular lecture. When we get to the end, you'll see the relationship between a small synthesized die cavity and the pad frame. So synthesizing this out, that's the end of that's where CMOS VLSI as it's kind of a general overview ends. And going any deeper goes into specific synthesis, optimization, pad frame generation, power consumption, all that stuff. So at this point, you should have a very good general overview of how this all works. Let me formally define die cavity as the space within the package where the cells are placed. So you have to know the size of your die cavity, and I left this out. Basically, it's generally proven that a square die cavity is the best area, just because. And actually, let me ask you guys: why do you think a square die cavity is best?
To maximize the amount of area.
Maximize the amount of area, and how does that apply to what? Why would we do this instead of, say, a circle or a rectangle?
Most of the stuff you want to put in the square,
Mm-hmm.
so you can bump it all the way against the edges.
Everything except bumping into the edges is correct. The thing that you're going to synthesize won't be along the edge. Oh. I actually, what I just explained is a big part of it.
It's easier to route the wires.
Yes. Easier to route the wires. And the reason why is if we did this as a rectangle, and we put one thing here, it's very possible that your floor plan will have a lot more cells that need to be accessed. Whereas if you make it a square, or you may even make it a smaller square like this, and you make it over here, your general floor plan is going to move it over here naturally. So the square is the best shape in terms of floor planning algorithms. We're not going to go into an example of a floor planning algorithm in this course, just because I don't think that algorithms is a requirement at this stage in your curriculum, or I think in double E at all. So in order to go into that level of depth in terms of floor planning algorithm, you would need to have a strong understanding of that. So
like optimization.
Yeah. Mm-hmm. But those algorithm is. Are you guys familiar with what's known as a heuristic? You've heard the word, but you don't know what it formally means. So a heuristic is what's known as approximation algorithm. There's some algorithms that's known as NP complete or NP hard. This problem is an NP hard problem, and what that means is that in a short, without going into too much detail, basically it's way too time consuming to actually solve. Or you would need infinite resources, or with the specific resources you can't solve them. So you can't come up with it, or you can't come up with an exact algorithm to solve it exactly every single time. That's a better way of phrasing it at this level. So what you try to do is you try to come up with an approximation algorithm that comes up with as close to a best solution as you can get. And so these are, so in order to really understand why it works, because sometimes you'll come up with a really good answer and sometimes you come up with a really not good answer based on the approximation algorithm, because sometimes you're going to get wacky results. But that's the purpose of it, is because you can't actually solve it exactly. And so that ties into NP equals NP, which I don't want to go into here, but generally what this means is that we're trying to come up with the best known solution. So an exact algorithm is Klein-Mikulski, QM reduction, you're familiar with that? However, when you're actually trying to synthesize that in billions of transistors, it becomes very, very time consuming. So there's actually an algorithm called Espresso, which does approximately the same thing as Klein-Mikulski, but may have a little bit of area overhead, but it calculates significantly faster. A QM reduction is not NP hard or NP complete, but it's important to know that if you're trying to do it, synthesize it quickly, or every single time you're trying to synthesize it before you check area, have floor plan, then place and route, and area optimization, power optimization, interconnects optimization. You especially when you're dealing with things like for example, magnetic QCA, which is a post-CMOS technology. Sometimes when you synthesize it, it can take days. So if you can come up with an approximation algorithm that comes with a relatively correct answer that reduces that to hours, that's where that kind of thing becomes important. So all that spiel to tell you why I didn't teach you something. Okay, so I alluded to this a little earlier today about channel ordering. So here we have two channels. We have channel A and channel B, right? So we are trying to first thing we want to do is we actually want to optimize this channel first, right? So if we optimize this huge channel first, we're not going to try to bring these as close together as possible. You can potentially optimize them at a wide width here, but once you do this, you can't go back and fix that. So basically, you want to optimize the short channel first and then the longer channels. So hopefully that's a short description of a long problem. The reason why, if you see, we're trying to create our slices. We want to try to reduce the amount of wiring it takes to get from point A to point B. And if we don't do this one first, what's actually going to end up happening is all these connected wires are going to get longer and longer and longer. Let's say if this was down here for some reason. So by optimizing the short channel first, we also optimize the longer channel, but it's not going to work the other way around. So that's why this channel ordering becomes important. And so we're formally defined channel ordering as the process of assigning areas between blocks that are used for interconnects. So we're going to use a min-cut slicing tree, and here is going to be our example I'm going to describe in a moment. Channel order uses a min-cut slicing tree to make a cut all the way across the chip between circuit blocks. So here, that's the example. And from here, we're going to continue cut until we actually have a tree. We cut pieces into two without cutting through a circuit block. So here's the example. So we're given a T-shaped junction between two regular channels. Show the sequence of cuts and draw this sequencing tree. So this is your sequencing tree, and this is the sequencing cut. So this is what's required for the example. Required to determine the proper channel ordering of the circuit block. So here's what's going on. First things first, we see that we can make a cut all the way across this channel here, right? So this is actually I'm going to zoom in just a little bit and put this in the middle. So we have this here, right? So the first thing we do is we see that we can cut this in half. Okay? So then, from here, we're trying to figure out from this cut, what's our most effective cut? Can we get all the way to an edge? Here we can. So next thing we're going to do is we're going to go this way. Right? So our second cut, so that this becomes our first cut, right? And then we make our second cut. So this first cut, we can access D, right? So the whole goal is we want to be able to access every possible cell. And so this hopefully this min cut will make why, will show you why having the different layouts, even with the same logic, can contribute to more wiring. So we make this first cut. From that cut, we can access D, right? Here, the second cut, we make this cut and we can access the A, B, C, and D, but we haven't quite gotten there uniquely yet. So from here, we can make two more cuts. Cut 3 is shorter, so we get to this one first. We make a cut all the way across, and that one allows us to access A and B without having to make any more further cuts, right? So that becomes, so let me walk through these steps again. We make our first cut, and here we've reached D, and that becomes cut 1, right? So then we reach cut 2 here, and so this is going to help us reach A and B, right? So this is 3, so this is cut 2 all the way down, but we get to this one here first, so that becomes how we reach A and B. Then we keep going, and then we reach cut 4. This is cut 4, and that allows us to reach C and E, as we can see. So now, when we are doing our channel ordering, this is going to be our min cut tree. So this is the minimum amount of distance required to reach every possible cell. Yes, Coleman.
I just don't see why you can't access A with the first cut.
Oh, no. Okay, let me, that's a good question. You have to, it's not that you can't access A. Let me phrase it properly, right? So here, you made the first cut, right? So now the whole goal is have you kind of gone through, completely surrounded it without hitting the edge, right?
Okay.
So here, we've cut off D from everything else. We haven't cut off A from everything else. We haven't cut off anything else. So that's where the min cut comes into play. So here, we've established that we can reach node 2, right? But we haven't cut anything off yet. So if we're going through again, we have our first cut, and we've determined that after that first cut, we've cut D off from every other cell, right? So that cut, those wires, we want to get to cell D. So now we make our we realize we have our second cut, and this gets all the way down to node 2 here, right? At the edge, at the wall. But the first thing we're going to do is we're going to kind of go slowly here, and then we get here, and we realize that we can cut all the way to the edge again, right? So here, by getting all the way here, now we've cut off A, and we now know that we can guarantee to cut off B if we get to the end, right? So now we've cut these guys off, but we haven't done C and E yet. So here we make our second cut. To node 1, we have node 2. When we go to node 3, that's when A and B come into play, right? Because here's node 3. And then we go a little further, we see we can get to the edge again, and that becomes cut 4. And that gets us to C. And then we now know that we can get to the end here, so then we can get to E. So if we were traversing this tree, we do something called depth first search to be able to see how we got it. So we go here, and we go right, and we get to D. Now we've reached the end of our tree. We go here, we're going to go left again, we go to C or E, then we get to the end of the nodes, we can go up, we go to A and B. And then we go all the way back. So that's how we traverse that tree to be able to reach all possible nodes. Yes, Terrence.
This might be a very dumb question. Why can't you make a cut all the way horizontal between A and B and C and E? Why you gotta come down?
Oh no, it's not horizontal. See how you cannot do that. It has to be a straight line. And the reason why it has to be a straight line is because of the min cut requirement. This is not a dumb question. Those are very good questions. because the whole point of this is we're trying to reduce the wire length. Okay? So if we come up with a min cut, then we can hit every possible part of D. And you know, because remember, it's all cut into bit slices that we're trying to optimize that particular area. So if we can come up with a min cut, then we can guarantee that we can get every single part, right? So then we get to these two, we figure out we can, along this min cut, then we can get a straight line to the edge. And actually, I'm going to show you an example here in a minute that should really answer your question in detail. Once we get down here, then it's kind of like, all right, I can see the end here, right? So now I'm kind of like, all right, so now I can see the edge there, and now I'm looking both ways until eventually I have a path here. I see that, okay, there's no other path there, so I know that these two are done, right? I can get down to this edge. So then I go down here, I see a little further, I can get C and E, and now here's the way it would work, because I think the next logical question is, how can I know that B and E are included? The answer is, I don't know yet until I've gotten all the way to the edge. So now, once I get all the way to the edge and I see that B there's no other cut, just the last edge, then I can include A and B in the same node, and then C and E in the same node. Okay. Yes, Jason? That's part of the algorithm. That's why heuristic, not up. There you go. That ties really well into why it's a heuristic and not an exact algorithm. Yes, Kevin?
Is it just this example? They're not always going to be binary trees, right?
No, they're not.
Okay.
And to answer you and Terrence's question, what happens if there is no cut? No cut, no cut, no cut. There's literally no way to get from one edge of the floor plan to the other. Again, here, no, we'd run into B. Here, we'd run into C. Here, we'd run into A. Here, we'd run into A. Here, we'd run into E, right? And so what they're trying to do here is they're trying to move this around until we actually get min cut. So now what's happening is they're moving cells around. So here on the left is the initial layout. We can't get all the way across. We can't get all the way across. So now it's like, let's see if we can move these around. We try again, still doesn't work. We try again, and we finally figure out a min cut solution. So what I probably should have defined this. That instance where there is no clear slice across the die cavity is known as a cyclic constraint. It's an instance where there is no clear slice across the cavity. And so what I state here is there's two solutions to the problem. Move the blocks until we obtain a slicing floor plan, or the use of L-shaped rather than rectangular channels. So here's the thing. Which one of these is better?
I think C.
You think C?
I haven't, but you didn't slice E and B or A and D.
Mm-hmm.
The A and D do straight across.
Yeah. So your second part of your statement there, what you're talking about, but there's actually ties into this correct answer. So turns out by using L-shaped channels, you actually can get to everything, right? So this is where heuristic comes into play. Right, so now you have a tree here. This just makes everything the longest possible. Right? So here, this is B is the compromise. So this is our initial layout. Man, these wires are long. This one is, we have a min cut, but man, this is an ineffective use of the die space because area becomes an issue here.
You got a huge chunk
You got-
empty space.
Yeah, good design requires good compromise. So this is where B in the middle comes into play. So does anybody have any questions about this?
I'm still confused, like
Sure.
why B is like better than A or C?
Okay, so this is a compromise between the two. All right, so A has our initial problem. Our first problem is the best way we can do it, ideally, is if we can come up with min cut slices, right? So we can't do this here. So we've moved everything around, and we figured out a way to finally do it. But here's the problem. In a weird sort of way, this causes some issues, especially if we want to communicate between A and C. Oh no, A and C is fine, but D and C versus B. See how it's an inefficient use of the space? We have this huge block here where nothing's happening. So that means we have a huge part of our clocking tree that's not being used at all. Right? So what ends up happening is you're going to try to optimize your area in this manner. So this is a trade-off between these two. This isn't always going to be the case. This is one instance. So the reason why I went on this whole spiel about heuristics is because there's no one guaranteed answer to this problem. Sometimes A might be what you're stuck with. Sometimes, you can actually come up with a min cut like up here and it works. Sometimes you have to make these L-shaped channels to make it work. There's no one right answer. It's based on your previous layout, what your design is. It's all dependent upon what you came up with at your spice level. And it's all driven by interconnects, parasitic extraction, and power consumption, and timing analysis. So you're juggling a lot there. Does anybody else have any other questions before we move on? Okay, so at this point, we've finally reached flattening. So I've been very adamant, don't flatten, don't flatten, don't flatten, don't flatten until you've verified it works, you've gotten your proper layout, you've tested everything, you've found all your errors in your different layouts, and then you flatten everything together. Flattening is then when you start saying, okay, so this is how we can use our area overlapping, this is how we can merge our polygons into cells, this is how we can actually get these to actually work, right? So once you've thoroughly tested it, that's when you can actually flatten. Otherwise, you're going to have a really bad day. You think getting 14 errors in a cell is bad. I've seen instances where it's thrown 1,000 when you flatten. So here we're going to define flattening as the process of merging polygons into a cell or multiple cells into a higher level of abstraction. So we were talking about abstraction earlier in the section. And so you're trying to basically, you either take a number of AND gates and XOR gates, and you put them into a full adder. It takes full adders and you merge it into a carry select adder, carry look ahead adder. Or you can take an adder and you can take a bit shifter, and you can put them all into an arithmetic logic unit. Or you can take your arithmetic logic unit and your memory and your registers and your controller, and you can merge it into a full cell. Okay? So there's all these different abstractions. Merging any of those is known as flattening. So what we're going to do here is we can actually do something called selective flattening. We can get around the problem that you were just asking about, Suprab, by selectively flattening cells together in order to try to create a min-cut channel. So we define this formally as the process of merging flexing cells in order to create a channel cut to remove a cyclic constraint. So we have a cyclic constraint. There's no clear cut across the DAG cavity. We merge some cells together, then we create one, right? So here we have A and E and C, right? So what happens is, what we're going to do is we're going to move the cells around so that A and C are now together. Then we merge them, and now we've created our first cut. So now we have a cut channel. Now we're trying to now we've reduced the number of L-shaped channels that we need. So again, this is all kind of a higher level, like floor planning is its own field. Right? And floor planning isn't just in CMOS. Floor planning is, as kind of alluded to earlier, is a huge aspect of FPGA design, of advanced digital systems, all of that. So basically being able to lay it out in a way that consumes less power and being able to meet your performance constraints all ties into floor planning. So does anybody have any questions on this before I move on?
Like when,
Yeah, sure, super.
If
Go ahead.
I move like F and D, if I interchange F and D, then like might be one entity might get a single element. So that it would be better, right?
Yes.
Okay.
Yeah, that's exactly right. Very good. Very good.
Okay.
Did everybody understand what you just said? Okay. Good. How many pages we got left here? So this is a good place to stop. So we're gonna, on next Tuesday's class is canceled. I will be on travel, but on Thursday we will be we'll conclude section 9, which will be the just to give you and that's CMOS VLSI design. So there's your motivation. You put all this work in a thing that's 1/10, it's 1/20th the size of a dime. But we will start at I/O, and we're almost there. Yeah, I/O and power planning. So we've gone over floor planning, and we'll conclude.